Hello everyone. Today we'll be doing problem 133. So there's a piston, frictionless one, no mass, no heat capacity, vertical one, has two equal halves. Each half has 1 mole of air and standard temperature and pressure P0. There's a load suspended from them and they push down. So this part will go down to here. So how large a volume does the compressed air in the lower part of the cylinder ultimately occupy if W is very large? So we'll do some assumptions. Here we have H, this is Y, so now there is H minus Y. And also I will assume the cross-sectional of the piston to be S, and we have the original temperature of T0 and the ultimate temperature of T1. So both of them has temperature T1. That is because it is well, we'll show that in the future calculations. So we shall write some equations now. First of all, the PV equals mu times R times T. So we have here, I'll indicate V as SH over T0 equals P1 times H plus Y S over T1. And it all equals to R. This is because mu R and mu equals to 1. And now, because the temperatures are identical, the piston is of no heat capacity, so it actually will ensure that the temperature of both parts is equal. And the second equation we have is about the energy. So in the ultimate standard, in the ultimate condition, the gravitational energy change is minus W times 8 times Y, and that equals to P0 times actually we should write it as this, CV times 1 times CV times T0 times 2. This is the original state. We should write here. Oops. To minus 1 times CV times T1 plus 1 times CV times T2. And CV here equals 5R over 2. This is because this the air, we see it as and dipole, dimolecular gas. So the CV equals 5R over 2, and we also have T1 equals T2. And second, we have the fourth equation, that is P2 minus P1 equals W over S. Equating them together, we'll get actually some things, but we will get eventually by Y over H equals to 35W squared plus 25 P0 squared A squared minus 5 P0A over 7W. So when the W is very large, it will be similar to this. So this is the final answer. there's not a lot of difficult things actually. The most important thing is to remember that when you are dealing with these kind of equation, always think about the second law of heat. So, and you should also know the exact difference between heat, internal energy, forces, work down, or something like that. So that's it all for today, and I hope to see you tomorrow.